Hello everyone, welcome to chapter 8. So in this chapter we'll talk about addition reactions and alkenes. So in this lecture we'll discuss the introduction of addition reactions and alkenes, and we'll see the difference between alkenes in nature and industry, and we'll see the difference between addition and elimination, and we'll see different versions of addition reactions and what type of addition reactions generally occur. In the first lecture, we'll cover the first 7 topics. In the second lecture, we'll cover the rest of the topics. So let's start with the first one, introduction to addition reaction. So what is an addition reaction? So an addition reaction is basically the opposite of elimination. In elimination, you lose a proton and a halogen. Here, you lose 2 elements at once. Here, in addition reaction, we are basically adding those 2 elements to the adjacent carbons. So between the pi carbons, we are going to add the elements there. So we are converting a pi bond into 2 new sigma bonds. So this is what we are doing here in terms of addition reaction. So what are the types of addition reactions that you will generally see? Number 1 is hydrohalogenation. Hydrohalogenation requires on one side the addition of hydrogen, on the other side the addition of a halogen. And the second type is hydration reaction, which involves the addition of a hydrogen and a hydroxyl group on the adjacent carbons. Hydrogenation, which requires addition of hydrogens. Halogenation, which requires addition of halogens on both sides. And you have halohydrin, which is hydroxyl group and a halogen. And you have dihydroxylation, which requires 2 OH groups to be added. So what happens in addition reactions? So the pi bond that is present in the alkene acts as an electron pair donor. And when you think of it as a base, when you have a base, think of it as a base, then the double bond will basically donate its electrons to the hydrogen and forms a single sigma bond and creates a positive charge. If it's as a nucleophile, it does the same exact thing and donates its electron pair, forms a bond with the atom, with the element, and creates a positive charge on the other side. So alkenes in nature and industry. So naturally occurring, in general, you will find acyclic alkenes. For example, allicin is an acyclic alkene that is responsible for the odor of garlic. You have geraniol, which is the main component used in perfumes isolated from roses. And alpha-farnesene, which is the natural waxy coating on apple skins. So these are some examples of polymers. Now, cyclic polymers are, for example, limonene is the one that is responsible for the strong smell of oranges, and cholesterol, the common compound that you already know, is the one that is produced by all animals, and it plays a pivotal role in many of your biological processes. Now, the carbon double bonds are often found in structure of pheromones. So pheromones, these are compounds that are commonly used in the mating process for biological animals. For example, this is a common compound found as a sex pheromone of codling moth. You have beta-farnesene, which is an aphid alarm pheromone. You have muscalure, which is the sex pheromone for the common housefly. So most commonly, sometimes we can use the compounds that can inhibit this behavior is to create the opposition, the compounds that replicate this behavior to make sure that to neutralize these compounds, to make sure that these animals do not grow out of proportion. So that is how population control is done for some moths and animals in general, to make sure that they do not breed too much. Now, in terms of alkenes, where do you find them mostly? Alkenes are the critical precursors in the chemical industry. Most commonly, you can find them from petroleum products, and 70 billion pounds of propylene and 200 billion pounds of ethylene are generally made from cracking petroleum each year. So when we start with petroleum, we have ethylene. From ethylene, you can make polythene and ethanol, and you can also make acetylene. You can make ethylene dichloride. You can make ethylene dioxide. From acetaldehyde, you can make acetic oxide. From ethyl dichloride, you can make vinyl chloride, and from ethylene oxide, we can make ethylene glycol, which is a really good solvent. And from vinyl chloride, we can make PVC. PVC is polyvinyl chloride, which is the common compound used in common household piping. And if you take propylene, you can make polypropylene, and you can also make cumene. You also have isopropyl alcohol and propylene oxide. You can make propylene glycol and acetone. Acetone is the common nail polish remover that you generally use. It's a good solvent. And propylene glycol is another common compound that is used in, for example, say wet erase boards. These are commonly compounds that you can use as solvents. Now, what's the difference between addition and elimination, and how do they differ in terms of their equilibrium? So, addition and elimination are equilibrating reactions, which means that one causes the equilibrium for the other. Now, let's take a simple example of which side it favors, because which side is favored, it always depends on the temperature. Now, the higher the temperature, the more important the entropy becomes, because entropy is tied to the temperature. Now, higher temperature means there is a bigger entropy term. When there is a bigger entropy term, we know that the chances of delta G being negative are much more often. And when delta G is much more negative, it's always a chance that delta G becomes the compound that you commonly end up using. Now, addition reactions are generally favored by enthalpy. You have sigma bonds that are generally stronger than pi bonds. That's the reason why sigma bonds are always favored. That's the reason why addition reactions are always favored. For example, if you take a common reaction of common addition reaction here of adding ethylene to HCl, you have 166 kilocalories per mole of energy on the left side. On the right side, you have 185 kilocalories per mole. We notice that delta H here is negative, which means that this reaction is exothermic. Because this reaction is exothermic, it is generally be the one that is more favorable. Now, addition reactions are not favored by entropy, but two molecules combine to form one product. So therefore, entropy is actually decreasing here, because when you have two reactors combining one product, you are decreasing the number of moles of gas. But at lower temperatures, enthalpy will dominate, and addition reactions are generally favored. When you go towards higher temperatures, entropy will dominate, and elimination reactions will be favored. So, for addition reactions, we need to use lower temperatures. So when you use low temperatures, it undergoes addition. When you use high temperatures, it undergoes elimination reaction. So let's take the examples. So let's start with the first addition reaction, hydrohalogenation. Hydrohalogenation involves the addition of a hydrogen and a halogen to the alkane. So the common ones that are used are HCl, HBr, and HI. You cannot use HF because HF is not a favorable compound to react it because it is too violent. Now, when you take an alkene and you have HBr added to it, this brings up the question. Notice that it is low temperatures. So it undergoes an addition reaction where hydrogen is bonded to the left carbon here and bromine is bonded to the right carbon. This brings up the question, what happens if the alkene is not symmetrical? Notice that here both of them have the same number of bonds, so that's fine. But what happens when you have an unequal distribution of bonds on each of these vinylic positions? So remember that this position is called as the vinylic position and this is the allylic position. So in the vinylic position, which vinylic position will the bonds go towards? Where will X go? Where will H go? So this creates two regioisomers. Now these two regioisomers are what we call hydroboration. Hydrohalogenation is a regioselective reaction, and it undergoes what we call the Markovnikov addition. What happens in Markovnikov addition is the less substituted carbon will get the smaller atom, the more substituted carbon will get the larger molecule. So in terms of HBr here, you have H and Br. H is the smaller one and bromine here is the larger one. So to understand the difference now, when you have smaller and larger, which side will it go towards? Now notice that on this vinylic position and on this vinylic position, which is more substituted. So whenever we say the term substituted, which has more bonds with carbons. Here notice that this carbon here only has one bond, but this carbon here has two different bonds. So the simpler way of putting this is that in a Markovnikov reaction, the less substituted carbon is the one with more hydrogens. The more substituted carbon is the one with less hydrogens. So hydrogen will always go towards the side that has less hydrogens. The one that has more hydrogens will always try to the one that has more hydrogens will be the side that hydrogen goes towards. The one that has less hydrogens will be the side bromine will go towards. So here let's consider that it is X. So the halogen will go towards the side that has less hydrogens. The hydrogen will go towards the side that has more hydrogens. Now here this side has one hydrogen here, but this side has no hydrogen. So bromine will go to this carbon and hydrogen will go to this carbon. So this here is an example of Markovnikov addition reaction. So in Markovnikov addition, the less substituted carbon will get hydrogen, the more substituted carbon will get the halogen. Now, what happens is that how do you achieve the reverse of this reaction? You can achieve the reverse of this reaction by using an extra compound in addition to the original compound. That extra compound is the peroxide. If you use a peroxide with HBr, it changes the regioselectivity to the opposite direction, where you will see anti-Markovnikov addition. So what happens in anti-Markovnikov addition? Bromine will go towards the less substituted carbon and hydrogen will go towards the more substituted carbon, provided you add a peroxide solution to the original structure. So this is the idea behind the problem here. Now the reaction mechanism must be different when you have peroxides that are present here. Now the important lesson here to learn is that the regioselectivity Hb of the hydrohalogenation can be controlled, and this controlled hydrohalogenation involves either Markovnikov addition or anti-Markovnikov addition depending on the presence or absence of peroxide. In presence of peroxide we have anti-Markovnikov addition. In the absence of peroxide we have Markovnikov addition. So pause the video right here and try to solve the second one. Let me do the first one. We have this structure here. Now, which is the less substituted carbon and which is the more substituted carbon? Those are the things that we need to do. So this carbon here has 1, 2 and 3 and 4 bonds. So there are no hydrogens here. This is the more substituted carbon. This becomes the less substituted carbon. So we know that hydrogen will go towards the less substituted carbon. Notice that there is no peroxide. So hydrogen will go to the less substituted carbon, bromine will go towards the more substituted carbon. So the structure will become this structure. So this is your final structure for the reaction. So this is how the product forms. So use the same principle now. Pause the video right here and try to solve the second problem. Now, how does this reaction occur? What is the mechanism? So the mechanism here is a two-step process. First, it involves proton transfer. Proton transfer is where the double bond attacks the proton and forms the proton bond first. So the carbon that has the less substituted carbon will be the one that attaches to the proton, and the positively charged carbocation gets attacked by the negatively charged bromine. So this here ends up becoming the final one. The second process is the nucleophilic attack. So this is the common process that you generally have seen already. Now the step with the highest activation energy will become the rate determining step. Here that step here is the formation of the carbocation. So the proton transfer process is the process that involves the higher activation energy. So that is the one that decides the rate of reaction. So unless the proton transfer occurs, the reaction will not go further. So this is the idea behind hydrohalogenation. Now in anti-Markovnikov pathway, because of the presence of the peroxide, the carbon will attack the hydrohalogen, but here the tertiary carbon, so the carbocation will always be the more substituted one, will be the one that gets the hydrogen, and the X minus will finally attack the main structure, result in positive charge, resulting in the formation of an anti-Markovnikov pathway. So in anti-Markovnikov pathway, you always end up with a secondary carbon intermediate. In Markovnikov pathway, we always end up with a tertiary carbon intermediate. So that's the only difference between the two reactions. the formation of the right carbocation. Now, which is more favorable is that secondary carbocations are generally less favorable and tertiary carbocations are generally more favorable. Remember that positive charge always likes to stay in the side that in the more substituted carbon. So that's the reason why this reaction involves more the formation of the Markovnikov pathway rather than anti-Markovnikov pathway. Now, hydrohalogenation can result in the formation of a chirality center if there is none at that point. For example, here there is the chance that this creates a chirality center. That chirality center formation involves two Markovnikov products. You end up getting both R and S in equal amounts in 50-50 process. So remember that here you get a racemic mixture. So you end up getting a racemic mixture. Now, why is it that it's 50-50? The reason is because it's already forming a positive carbocation, so the halogen can attack on either side. So that's the reason why there is a equal chance of forming both the chiral configurations. Now, hydrohalogenation can also result in the formation of rearrangements where the carbocations can rearrange if they try to become more stable. Now, let's start with a primary alkene. So, in a primary alkene, you have here the carbons here are both primary carbons. Now, the positive charge that forms here, if you take the Markovnikov pathway, will be this here. But this positive charge adjacent to it, it has a tertiary carbon. So, what will it do now is that this will try to move here and push the hydrogen to the left side, resulting in the formation of a tertiary carbocation. Thereby, the chlorine will attack the positive charge, forms the product. So when this alkene undergoes hydrohalogenation, what is happening here is that the secondary carbocation could rearrange itself to a more stable tertiary carbocation. So this is the idea behind the compound here. Now, when carbocation rearrangements can occur, so the rearrangement product will always be the one that's more favorable. So the formation of the one that undergoes rearrangement, so will always be the one that if the more the rearrangement, so the chance, if there is a chance of rearrangement, that's the product that will form. Next, let's talk about acid-catalyzed hydration. So what is a hydration reaction? We are adding a water molecule, so where we add hydrogen on one side and a hydroxyl group on one side. Acid-catalyzed hydration is a Markovnikov regioselectivity, so which means here again, the more substituted carbon will get the OH group, the less substituted carbon will get the hydrogen. So here to add that hydrogen and OH we need an acid. So that acid favors the reaction for it to occur clearly. So this reaction involves the addition and creates the OH group on the more substituted carbon and a hydrogen on the less substituted carbon. Now the common catalyst that is used is sulfuric acid, and the sulfuric acid is a typical catalyst that is used for this reaction. Now the OH here that is added to the more substituted carbon of the alkene. So the more substituted the carbon, the faster the reaction. So if the more substituted carbon is much more substituted, the more substituted it is, the faster the reaction. For example, a primary one would be, if you consider that to be a relative rate of 1, a secondary one would be 10 to the power 6 and a tertiary one will be 10 to the power 11. So this is how the rate of reaction increases with the more substituted carbon. Now the mechanism of this acid-catalyzed hydrogenation here again involves, the first thing is proton transfer, where the double bond attacks the proton and attaches itself to the less substituted carbon and it creates a carbocation. The carbocation then gets attacked by the water molecule and it undergoes a nucleophilic attack. Finally, after rearrangement, it creates the formation of the hydration product. Now, depending on the type of acid that you use and the concentration of the acid that you use, the reactant and the products of the hydration are generally in equilibrium. So we exploit the Le Chatelier's principle to control the equilibrium on which side to favor. Now, under dilute H2SO4, where you have more water molecules, it undergoes addition reaction. Under concentrated H2SO4, when there is less water, it undergoes the elimination reaction. Now, if we are synthesizing an alcohol from an alkene, we will generally use excess water. If we are synthesizing an alkene from an alcohol, we would generally only use acid and not add water to the reaction. Now, the stereochemistry of hydration is analogous to the hydration for the same reasons. for hydrohalogenation for the same reasons here. Here also you have a chirality center that is formed, and you will still get 50-50 mixture of R and S. The reason mainly is because you have a carbocation formation. Because the carbocation is already stable, the chances of it being attacked on either side is the same. That's the probability is the same. That's the reason why we end up with a 50-50 product. Next, what other kinds of reaction can we do in terms of hydration? The other one is oxymercuration and demercuration. So Markovnikov hydration has limited application, and rearrangements will occur, giving the mixture of products. So that's the reason why we can use oxymercuration and demercuration. The only reason we use this reaction is that there is no rearrangements. The product that forms will always form the final product. First thing that happens to the alkene is there is an OH group attachment and a oxymercury attachment. Under demercuration will end up with the final product of no rearranged product. So here we use a compound called mercury cation, so mercuric acetate, which creates a mercury cation. The mercury cation is the one that acts as the intermediate product to create the no rearranged product. So first you have the double bond attacking the proton and attaching it to the less substituted carbon, and then the mercury cation will attach itself to the other side. So here first what happens here is that the mercury cation is the one that gets first attached and creates the positive carbocation, and finally creates what we call a mercurium ion. Mercurium ion is the reason why it doesn't undergo rearrangement. If you take a general addition reaction, notice that the positive charge is free to rearrange. That's the reason why this does not rearrange. Now what happens when the nucleophile comes and attacks the partially positive charged carbon? It attaches itself to the nucleophile. Finally, we use sodium borohydride to replace the mercuric ion with a hydrogen using the free radical mechanism. So these are two things that you need. First is mercuric acetate and water, and the second part of the reaction we need sodium borohydride. So these are the things that you need. So hydroboration, the next one is hydroboration and oxidation. Hydroboration and oxidation is the same hydration reaction, but it involves the anti-Markovnikov region selectivity. Here we use borohydride and THF, which is tetrahydrofuran, and you have in the second part of the reaction we use a peroxide. Remember that peroxide is the reason why it undergoes the anti-Markovnikov pathway. So whenever you have a peroxide, there is a high chance that it undergoes Markovnikov pathway. So here the less substituted carbon will get the OH group, and the more substituted carbon will get the hydrogen. So this will be the major product that ends up forming. So this is a two reaction sequence. First thing that happens is that once the alkene is attached, it undergoes the formation of enantiomers. So it's stereoselective, so the hydrogen and the OH are added in the syn fashion. Syn here means that both of them are added on the same side, either on the upper side or the down side, and you cannot observe the anti-addition where one goes on the top and the other goes on the bottom. You cannot observe that in hydroboration and oxidation. Here, because the carbocation has the same geometry as that of a sodium borane, that's the reason why it creates the anti-Markovnikov pathway. And finally, the active reagent here is the combined product of BH3 and THF. That's what is the final one that creates the anti-Markovnikov pathway. So finally using the pathway to create the transition states. So what happens here? The OH group attaches onto the one carbon, the less substituted carbon, and the hydrogen will attach to the more substituted carbon. So this is undergoing Syn addition, which means that both of them will attack on the same side, either from the top or from the bottom. That's the reason why the geometry is either always upper or always lower. So here you have two chiral centers. It can create two chiral centers here because it is creating a Syn addition, and you get a pair of enantiomers where hydrogen and OH are on the bottom and hydrogen and OH are on the top. So you have two different isomers, enantiomers that you end up with. So pause the video right here and try to solve this problem. Next, let's talk about catalytic hydrogenation. So hydrogenation is basically the process of adding hydrogen to the double bond. So it requires a metal catalyst, and you have an alkene that is going to be converted into corresponding alkane. So you're basically removing the double bond and adding two hydrogens to each of the carbons to the double bond. And you use a metal as a catalyst. Most common metal that is used here is platinum or nickel, and it depends on the metal that we use, how the reaction will progress. Now these are stereospecific reactions, which means that there is only Syn addition that occurs, which means if you have a chiral center, then both the hydrogens are either added on the upper part or on the down part. So you end up getting two chirality centers and you get stereoisomers from Syn addition. Now without a metal catalyst, the addition of hydrogen is too slow because of the high activation energy. But with the catalyst, you reduce the energy to such a low value that the reaction will occur really fast. How does the catalytic hydrogenation work here? Is that when you have molecules here, the metal plate attracts the hydrogens and traps the hydrogens in one place, and when the molecules, the alkenes, come and attach themselves to the metal basically has hydrogens that it sticks onto the alkene, resulting in the formation of addition. This is the reason why it has Syn addition, because the molecule is getting attached to the metal on the same side. That's the reason why it undergoes Syn addition. Either it touches the metal from the bottom or it touches the metal from the top, and determines the final stage, and you end up with a same product. Because both structures here are the same, we can consider that this is a Miso compound. So because of the Syn addition here, it will not produce a pair of enantiomers, and a Miso compound will be the one that ends up forming. Now what are the types of catalysts? We have homogeneous catalyst, which does not involve in the reaction medium like platinum or palladium. You have a heterogeneous catalyst where it does involve in the reaction medium, accomplished by using a ligand with the metal. So you have Wilkinson's catalyst. Wilkinson's catalyst is basically rhonium with 3 triphenyl phosphate groups attached to it and a chlorine, and this also creates the same idea here, the same reaction here, and finally forms a product. So recall that whenever we have the creation of one or two chiral centers, you have a mixture of enantiomers. Here also you end up with a mixture of enantiomers rather than, so it creates not just one chiral center, and this is the reaction where it creates 2 chiral centers. Now if you use a chiral catalyst, it is possible to synthesize only one enantiomer. So this is accomplished by replacing the phosphine ligands on the Wilkinson's catalyst with the chiral phosphine ligands. Replacing them with chiral phosphine ligands creates the particular chiral compound that you want to form. And you have the next one, which is asymmetric hydrogenation, which is an asymmetric reaction where you add hydrogens on different carbons with a different structure formation. So the first reaction that was developed was by William S. Knowles. He developed a synthesis of L-dopa using asymmetric hydrogenation as the key step. So this was the reaction that earned him the Nobel Prize in 2001. And you also have Roji Noyori, who showed that the chiral ligand BNAP also offers one enantiomer with high selectivity. So he also won the Nobel Prize with Knowles in 2001 for the